Hello everyone, welcome to the live class. So please let me know in the comments whether everything is alright, like the audio, video, slides, everything is fine. And then we will start the discussion. That's very good. Okay, so guys, today we are having a session on atomic and molecular physics, and we are going to consider one of the very important points in today's session, based on which there are great chances that you can expect the questions in your upcoming exam too. So that's gonna be related to spectroscopic terms. You may be familiar with the spectroscopic terms, but if you are someone who is having any type of confusion in the spectroscopic terms, so don't worry, today's session is going to help you a lot, and we are going to take various examples, many methods, okay, and different concepts I will let you know, which will help you to make or to get the answer of such type of questions very easy, clear, and will make the questions easy and simple for you. So it will be possible for you to answer such type of questions in very less time after attending this today's session. Now let's quickly start the discussion. So the first point I'm going to consider, that's gonna be related to the equivalent electrons and the non-equivalent electrons. Okay, two different things we are considering. One is equivalent electron and the other one is non-equivalent electron. Clear? So firstly, you will tell me in the comments, do you know something about the equivalent electrons? That what type of electrons will be known as equivalent electrons and what type of electrons will be known as non-equivalent electrons? And attend this session till the end, because many important points one by one we are going to consider in today's discussion, and everything is gonna be very important for you. So what we mean by the equivalent electrons and what we mean by the non-equivalent electrons, whatever you know about it, just quickly mention it in the comments, and then even I am going to tell you exactly how you will identify this thing and how you will find the spectroscopic terms then. Okay, you don't know about it? Very good, Kirti. Okay. That's very good. Okay, let's take some example. Okay, very good. All physics exam. Let's talk about it. See guys, if we are going to talk about the equivalent electrons, like the examples I will give you, it's gonna be S2. Okay, S2. How many electrons are present in the S orbital? 2 electrons. And are these electrons are equivalent or non-equivalent? So whenever you will get any term written like this, S2, P2, how many electrons are there in this case? 2. Okay, in the p orbital. So again they are equivalent electrons. Then P4, I'm just telling you about the different terms. Clear? So how many electrons are there? 4. All the 4 are equivalent electrons. Clear? Then if we are going to talk about D3 or D5, so all these are what? The equivalent electrons. Because if we are going to talk about the n value, if I am saying it's 1s2, clear, I can write 1s2, 2s2 like that. So the n, that is principal quantum number, will be same, okay, for that particular orbital and all the electrons present there. Clear? So in that case, what will happen? You will say these are equivalent electrons. When I will say you need to consider sp, okay, I have taken different orbits here, S and P. Clear? So in that case, this is gonna be the example of non-equivalent electrons. Clear? Or pd. So we are considering one electron in the p orbital, one in the d. Even the principal quantum numbers or the L values are different. Okay, so that's how you will consider it. Even it's not necessary that always the L values will be different only. No, they can even tell you, like in the previous years in CSIR net physics exam, we had the question in which they have mentioned that there are two non-equivalent p electrons. That means you will write these are the two non-equivalent p electrons. Okay, so it's not necessary that always just sp, pd, only these things you will have. You can even have ss, pp, dd, like that. So in that case we consider the principal quantum numbers will be different. Okay, and in these cases already the L is different, even the N can be different. Clear? So that's how you are going to consider. The first examples, first few cases which I have shown, they are for the equivalent electrons, and the next three which I have written, they are going to be for the non-equivalent electrons. So once you know that which one is going to be equivalent and which one is going to be non-equivalent, now you need to know that what exactly is a spectroscopic term and what are the steps you have to take to find the spectroscopic terms corresponding to equivalent electron case or the non-equivalent electrons case. Okay, let's talk about it. Wherever at any point you will have any doubt, you just need to mention it in the comments. Okay, and we'll talk about that point. Yadav, Jamuna, these sessions will be helpful for the TIFR exam too. Okay, now till now, is there any doubt anybody is going to have? Any doubt? Please let me know in the comments. Everything is clear? That's good. Now let's talk about the spectroscopic term notation. If we are going to talk about the general spectroscopic term, okay, how we show it, how we denote it, how we will write it, let's talk about that point. Also guys, the frequency of the questions from the spectroscopic terms or for finding the ground state, okay, from these points there are great chances you can expect the question from the atomic and molecular physics part. So that portion we are covering today. If somebody is preparing for the exam and if he or she will cover up this portion, okay, there are great chances you will be able to solve all the questions you will have or you already had in the previous years in CSIR net physics exam or even in any other exam from these points. So now the general spectroscopic term, if I am going to consider, for that we are going to have S plus 1 Lj. This is how we write the spectroscopic term, where this S is what? This just small s is representing the spin. Okay, this one is gonna be the angular momentum quantum number. L will be related to orbital quantum number. How we will write those values, what will be the steps you have to follow, what type of questions you will have, everything we will consider. But if I'm going to talk about the value of J, which is angular momentum quantum number, its values will lie from, or it will have the values from L minus S to L plus S. And the gap or the difference you have to take of 1. How? If it is gonna be, let's say from 0 to 2. So how many values it will have? 0, 1 and 2. All the three values you have to consider. That means the gap or the difference in the values should be just of 1. Okay, so that's how you have to consider it. I've just given you one example that 0 to 2 if you are getting here, then how you have to consider the values of J. Okay, so this is the normal symbol for the spectroscopic term. Now the point is this 2s plus 1, somewhere you will see it will be shown with the capital S. As you can see, all the symbols we are taking capital in this, so we even show it with capital S. This capital S represents the multiplicity. Okay, it is known as the multiplicity. If somebody wants to note it down, even you can note it down if you don't know about it. Clear? And further, I'm going to consider the cases for the non-equivalent electron and the equivalent electron in this today's session, so that everything will get clear to you. Let me know if there is any doubt anybody is having till now in the discussion. Sirsa, how the P and P that we have already written like this, P and P is gonna be non-equivalent electron because the principal quantum number corresponding to that can be different. L is same but principal quantum number, जैसे यहाँ पर n की वैल्यू आप ले लें 2 और दूसरा वाला 3 हो तो 2p and 3p, ठीक है, तो principal quantum number is gonna be different and that's how you can say it's non-equivalent electron case. Clear? So various situations can be there, and once they have mentioned it, because this type of previous year question we already had, if you will check the previous year questions you will get it. Clear? So in that case they have clearly mentioned it in the statement that consider two non-equivalent p electrons. Clear? So then we have to follow the process which we consider for the non-equivalent electrons case. Done? Clear? Guys, multiplicity is just 2 into spin plus 1. We'll apply it in the questions and you will get to know about it clearly. Now, after knowing about the general spectroscopic term, let's consider or let's start with the non-equivalent electrons case or the process. Okay, so let's consider that first. I will explain you one example. I will tell you all the steps, and for the second case, you have to find the spectroscopic terms. So please focus on each and every step, and once you are going to focus on each and every step, you will get everything clearly. You will not make any mistake anywhere because the process or sequence is gonna remain same. Okay, so can we start the discussion about the non-equivalent electrons case? Are you all ready for that discussion? Done? General spectroscopic term, how you will write and what is going to be the process for that, that's what we have considered till now. Let's consider the first case for the non-equivalent electrons. Okay, I'm going to take the example of SP. Anytime, even the 3 can be given to you, SP and D, but right now when we are starting the discussion we will take with just 2 cases. Okay, so 1 electron in S and 1 in p orbital. Clear? So in this case what you have to do, your step number 1 will be, for 1 electron which is present in the s orbital, what will be the spin for the 1 electron you can consider? That will be spin. Write for s orbital case and write the values for the p orbital case. Clear? Only one electron is present there. Focus on the steps and the process. Done? Spin S1. Let's say for the s orbital spin we are writing S1. What will be the spin for the 1 electron? Only half. So write it here. S1 is equal to 1 upon 2. What about this one? S2. What will be that? That will be equal to half. Okay, again for 1 electron. So electron is generally going to have the spin. We consider it half in general. So that's what I have written here. Spin for 1 electron which is present here, half. Spin for 1 electron which is present here, half. Clear? Now write the values of orbital quantum number. If I'm talking about the S case, what will be the L value? L1. Let's say S, P, D, F. If you are going to consider their sequence, S, P, D, F, the values of L will be 0 for S, 1 for P, 2 for D, F, 3. Okay, even for G you will write 4. So in sequence S, P, D, F, G. Okay, or even more if you will consider. So these are the values of L. What is L1 here? For S it's gonna be 0. Okay, it's gonna be 0. For P, L2, let's say it's gonna be 1. Clear? So L1, L2 you have noted down. And this case we are discussing for the non-equivalent electrons. What do you need to do after this? You will just consider a general S. S1, S2 you have noted down. Now you need to write S. What will be S? S will be S1 minus S2 2 S1 plus S2. That's gonna be the value of S. What is S1? Half. What is S2? Half. S1 minus S2 will be what? 0. S1 plus S2 will be what? 1. Okay, half plus half will be 1. And as I've told you, the difference in the values should be just 1. Okay, so 0 and 1 already having only one difference. Keep it as it is. These are the values of S you have got. Okay, next thing. Same for L. Get the L, which will have the values from L1 minus L2 to L1 plus L2. Clear? So what will happen now? See, 0 minus 1 to 0 plus 1. What you will get? It's gonna be just 1. You can write it twice or just write it once. Clear? In that case, now you need to make the, see, the combinations. How? The value of L is just 1. Okay, and the value of S you have got, that's 0 and 1. If you want, you can make a table. It will make the thing simple and easy for you. Note down L values. So only one we have got. It's okay. Okay, so write it. I'm not writing by repeating it because I am having two values of S. So I will take it one by one here. That's gonna be 0. S is equal to 0 and S is equal to 1. That's why I've noted down it twice. Clear? So now the value of J. What will be the value of J? J is equal to L minus S to L plus S. Okay, so L minus S to L plus S, and that's 2 in mod L plus S, which means 1 minus 0 to 1 plus 1, 1 plus 0 in the mod, you will just get the value 1. Again, 1 minus 1 to 1 plus 1. How many values you are getting? 0, 1 and 2. Because 0, 1 minus 1, 0. 1 plus 1, 2. But the gap or the difference of 1 should be there. So that's how you are getting 3 values, 0, 1 and 2. Clear? So you have got to know about the J values. You know about the L value. You have got to know about the S values after considering S1 and S2. Now your next step will be that you need to write the spectroscopic terms. Okay, sometimes they can ask you the question that how many spectroscopic terms will be there in this particular case. So total number of terms you need to tell. They can ask you which of the following will not be present in the spectroscopic terms you will get from this particular structure. That kind of question even they can ask you. So right now, once you will learn to find all the spectroscopic terms, you will have an idea about it. You will easily be able to solve any such question. Clear? So let's write the final spectroscopic terms right now. See, you know the spectroscopic term notation is 2 into spin plus 1 Lj. Now I'm going to tell you how you will write these values. Clear? Focus, and I will even check your comments. If you will have any doubt anywhere, you can tell me and we will consider that point too. Clear? See, 2s plus 1 Lj. What is a spin here? See, spin, the first one, first case you will take 0. So 2 into 0 plus 1. 2 into, when s is equal to 0 you are taking. 2 into 0 plus 1 is 1. What will be L value? It's 1. So for L is equal to 1, what value you are having? P. Clear? So L is equal to 1 means P. So capital P in place of capital L. Capital letters you need to write, everything will remain same, just make this change. J, what are the J values you have got corresponding to spin 0? 1. So write it here, 1P, 1, comma. For S is equal to 1, when you will consider it. Here is the S is equal to 1 case. 2 into 1 plus 1 will be 2. 2 into 1 plus 1 for S is equal to 1. What is the value of L? 1 itself. For 1, it's P. Write it here. J values 0, 1, 2. If the question is how many spectroscopic terms you are getting from here, so how many? What is going to be the answer? How many spectroscopic terms we will get from these two non-equivalent electrons? You can mention it in the comments. Oh, 2 into 1 plus, okay, it's 3P, right? Done? 2 into 1 plus 1, that's 2 ones are 2 plus 1 3. Clear? Now let me know how many spectroscopic terms we are getting from here. Total different answers, 3 4 3 4 4. Very good, very good. Okay, so guys, total spectroscopic terms are 4. Okay, one is 1p1, then 3p0, then 3p1 and 3p2. 3 from here and 1 from here. Total spectroscopic terms are 4. Okay, that's how you are going to get it. Now I am going to give you one question and you need to answer it. Just follow the same process or same steps and tell me the spectroscopic terms, the number of spectroscopic terms you will have in this particular case. Okay, two non-equivalent electrons. Let me know the number of spectroscopic terms you are getting in PD case. Find it with the complete process I've explained you. Okay, because you can't memorize them or you can't check it in the exam by writing all of them together. So you have to find it out. So find the all spectroscopic terms and let me know exactly how many spectroscopic terms you are getting for PD case. If there will be any doubt or difficulty, you can tell me about it. I will consider that point. Once you will get it done, you can mention it in the comments that these many numbers you are getting. For the PD case, you need to solve. Okay. If you will have any doubt or difficulty anywhere, just mention it in the comments once. That's very good, Kirti. One answer till now. Very good, Jyoti. Very good, Shahana. Very good, Shraboni. Very good, Yashika. It's 1. For P, SP 0 1, L1 1, L2 2, (1 minus 2 to 1 plus 2), it's gonna be 1 2 3. 3, consider the spin 0 and 1 both. 1 2 3 I have written from here. Clear? So that's what I have considered. And very good, Yashika, Kajal, Sangwan, Machi. Very good, Monica. Very good, Priyanka. Done. And next point. J is equal to L minus S. Oh, sorry, it's gonna be L minus S to L plus S, which means you will get 1 minus 0 to 1 plus 0. It's gonna give you just 1. 1 minus 1 to 1 plus 1. The gap or difference of 1 should be there. So 0, 1, 2. Okay. 2 minus 0 to 2 plus 0, just 2. 2 minus 1 to 2 plus 1, 1, 2, 3. Then you are going to have 3. Then you are going to have 3 minus 1 to 3 plus 1, which means 2, 3 and 4. So when I want to know about the number of terms, because corresponding to different spins we are getting different values, so we can count it like this: 3, 6, 9, 10, 11, 12. How many number of terms we are getting? 12. That's it. So even if you are getting an idea that okay, all the terms will be different, directly you can answer it's 12. If you want to write all the spectroscopic terms, you can. What is the value of L here? 1. For 1, it's P. Okay. For 2, it's D. For 3, S, P, D, F. It's F. Now I will write it twice. Why? Because spin 0 to multiplicity will be different for 0 and 1. So P and P. So for 0 spin, always 2 into S plus 1, which means 2 into 0 plus 1 will be 1. Okay. For spin 1, it's gonna be 3. Clear? So 1D, 3D, 1F, 3F. Clear? And then corresponding to spin 0, we have got 1 only. So 1P, 1. Here we have got corresponding to spin 1, we have got 3 terms: 0, 1, 2. Even if you want, you can write it like 3P0, then 3P1, then 3P2. Okay, you can show it in the 3 different terms, but you can even write it like this: 3P0, 1 and 2. Clear? Then 1D, how many values you have got for spin 0, 1, so 1D, 2, 1, 2, 3. The corresponding J values you have got now, we are just writing that. Then 1F, 3, 1F, 2, 3, 4. So now you can count total 12 terms in this way. Okay, that's how you are going to get it. Done? Clear? Is everything clear till this point to everyone? How you will find all the spectroscopic terms and how you are going to solve it completely? Everything is clear to everyone? Done? Clear? Now let's talk about the next type of question you can expect from the spectroscopic terms. That's gonna be for the equivalent electrons case, because that's gonna be just one case you will have. Okay, how you will find the ground state spectroscopic term notations, we are going to talk about that case. Okay, so let's talk about it. Clear? Jyoti, that is the same thing, but it was just a general representation. Instead of writing all the 3 terms separately, we were writing just one single term, and we know about it, that how we have written that. Clear? So it will be easy for you to consider. Now next point, if I am going to consider here, that's gonna be related to how you will check the ground state. Okay, so for that we are having the Hund's rule. Clear? Now what are these Hund's rule? Let's consider them quickly and then we will talk about the related questions. Even we will talk about the equivalent electrons case. Clear? Guys, whenever for any spectroscopic terms you want to find the ground state spectroscopic term, some number of terms you are having, but you want to consider which one of them is gonna be ground state. So let's take the first example here initially, and then we will talk about this thing, that how you will consider the ground states. Okay, for example, let me just give you one example right now. You can consider the terms, let's say 1s0 and 1d2. The first point I will explain with one example, that is 1s0 and 1d2. Is it 1d2? No, I will consider 2d 4s 1 by 2. Let's consider that one because I want it to be different. Or let's take 3f2. Any two things, I just want the multiplicity to be different. Okay, so let's say 4f2. Random example I have taken. Clear? I want you to find the ground state spectroscopic term if the two terms have been given, A and B. So which one will be the spectroscopic term for the ground state? Clear? Now the first point in the Hund's rule says that the largest capital S, which means the largest multiplicity. Capital S means what? This 2s plus 1 term. Okay, you need to compare them. If they are different in the different spectroscopic terms given to you, then whatever is the largest 2s plus 1 value, that will have the lowest energy, which means its energy will be minimum, and which means it's a ground state spectroscopic term. I'm repeating the statement once again. Largest 2s plus 1 value will have the lowest energy. And anytime if you are having many number of spectroscopic terms, then firstly you will see whether all the 2s plus 1, which means multiplicity, they are different or they are same. So firstly you will observe that point. Okay, so which one is gonna have the minimum energy in this? Which one is gonna be the ground state spectroscopic term? A or B? Very good, Kirti. What about others? Is that clear now? So largest 2s plus 1 value or the multiplicity will have the lowest energy. Okay, so that means this one, which is 4, which is largest one, okay, will have the lowest energy. And when the multiplicity is different, you don't need to observe anything else. But now the point is, let's come to the next point. If it is 4f, we will summarize all the points at the end. 2, 3, 4 and 1 S 0. Okay, let's consider it. Or you can say if these two terms you are having, clear? Now the multiplicity is same. I have taken the random example right now. So let me know now in the second case, which one will have the lowest energy, A or B? In the second example. And the examples we are taking randomly here, but I want to make the concepts clear to you. That's very good. And what is the rule? The rule is largest L term will have the lowest energy, like S, P, D, F. Okay, so S is having the L value equal to 0, P is having the L value equal to 1, D is having the L value equal to 2. Okay, so S, P, D, F. That's what you are going to have. Now the point is, since you can't compare with the multiplicity term right now, as it is 1 here, it is also 1 here. We can't compare with the multiplicity. So we will observe the L values then. Okay, what we mean by L? S. When we write S, L is equal to 0. For L is equal to 0, we are having S. For L is equal to 1, we are having P. So largest L term will have the lowest energy. So which one will have the lowest energy? That's gonna be A, okay, or 1P2. The first statement was largest multiplicity, that means 2s plus 1 value will have the lowest energy. Second point is largest L will have the lowest energy. If the multiplicity is same, you can't compare with that. You will have to check for the L values after that. But now I'm going to take another example. We will summarize all the points. Okay, but let's consider with the examples first. After that, we will summarize the points. 4F, 2, 3 and 4. Okay. Now 4F, 2, 3, 4 when I am writing, here you can consider these are the three terms. Basically 4F2, then 4F3, then 4F4. Okay. Now you need to tell that A, B, C or D, which will have the ground state or which is going to represent the ground state spectroscopic term, A, B, C or D. which one is going to represent the ground state spectroscopic term? Very good, Shahana. Very good, Jyoti. Very good, your blessings. Very good, Payal. Very good, Monica. Okay, very good, Karishma. Very good, Deepika. Very good, Subramanyam. Very good, Kirti. That's the point. Very good, Shaboni. Very good, Priyanka. Guys, basically you can't answer it with only this much information. You need to know about the configuration now. Okay, most of the students has considered, okay, largest 2s plus 1 is going to have the lowest energy, largest L is going to have the lowest energy. Now the largest J will have the lowest energy. It will be the case, but not always. So when it will be the case, let's talk about it. See, in this case, when you have to answer with the J values, because you can see, if you are comparing the multiplicity, so largest multiplicity will have the lowest energy. 3 terms you are getting with that, you can't answer it. All the 3 can't represent the lowest energy. Then what you will check? Then you can check the L values, but they are also same, F here. Then you can't answer with that too. Now what is there? That is the J value, that is 2, 3, 4. So there are 2 possibilities. Now if I am talking about the case D2, okay, it is what? It is the less than half filled case. In the d orbital, how many maximum number of electrons can be there? 10. Okay, but right now it's just 2. So less than half filled case. Whenever it will be the less than half filled case, lowest J value will have the lowest energy, which means 4F2 will have the lowest energy. But in which case? In this case. Okay, but when I'm taking the example of D8 or D7, which is more than half filled. Why? Because total number of electrons can be 10, and right now how many electrons are present? 8. So more than half filled, more than half filled, largest J value will have the lowest energy. Okay, so what is the largest J value? This one, 4. J is the largest in this case, so then it will be the lowest, or the ground state energy. I hope it will be clear now. Okay, so without configuration you can't declare it that what is gonna be the case. Normally students are going to have the doubt that okay, but what about exactly half filled case? I will tell you about it. Also guys, as we are considering the more than half filled case, that even works for the inverted multiplet. Inverted multiplet means, let's say you are getting D8, but you are solving it by considering D2. Okay, why? Because the inverted multiplets are going to have the same spectroscopic terms. That means, now what I mean by inverted multiplets, firstly let me clear that point to you. See, D8 is written. How many maximum number of electrons you can have in the d orbital? Total 10. Okay, if you are going to subtract this 8 out of total number of electrons you can, or the maximum number of electrons you can have in it, so 10 minus 8, which will give you D2. Okay, D2. So spectroscopic terms which you will get either from D2 or from D8, they will be same. But to find the ground state, when you will apply the Hund's rule, your ground state will get changed, because if one is more than half filled, another one is less than half filled case. So the spectroscopic term for the ground state will get changed, and the rule I have told you for the more than half filled case, that will work for the inverted multiplet situation as well. That means that when you are having D8 but you are considering D2, then also the more than half filled case is there, but you have considered it D2 by taking the inverted multiplet. So same rule you have to apply, that is more than half filled case, the largest J value will have the lowest energy basically. Okay, and in this case, if you are taking the normal multiplet, normal means what? When you are having D2, you are taking D2. When you are having D8, you are taking D8. Okay. or the lower less than half filled case. So I would say in the inverted and the normal multiplates there are chances somebody can get confused, so you can directly consider it less than half filled, more than half filled, only that one. Okay, and somewhere if you will have some difficulty, then you know that okay, something like inverted and the normal multiplate situation is also there. Okay, so you will be able to tackle such type of questions as well. Any doubt anybody is having till this point? श्रवोनी, वो मैंने आपको एग्जाम्पल दिया है कि अगर D2 हो या D8 हो या P2 हो तो क्या उसका आपको कैसे पता चलेगा, और वो आएगा कैसे, इलेक्ट्रॉनिक कॉन्फ़िगरेशन जब आप लिखेंगे ना तो वहां से आएगा, जो लास्ट वैलेंस इलेक्ट्रॉन्स जिसमें प्रेजेंट होंगे वो आपको कंसीडर करना है. गाइज लेट मी नो इफ देयर इज एनी डाउट एनीबडी इज हैविंग. If there is any doubt, please mention it in the comments. We'll consider that point. Done. Let's summarize all the points we have considered here. Point number 1. Largest 2s plus 1 value will have the lowest energy. Largest multiplicity term will have the lowest energy. Point number 1. Point number 2. Largest L term will have the lowest energy. Point number 3. If we need to compare with the J values, firstly we will check whether it is more than half filled case or a less than half filled case, and then if it is more than half filled case, largest J value will have the lowest energy. More largest. Okay. If it is less than half filled case, the lowest J value will have the lowest energy. Less than half filled, lowest J value. Okay, that's how you can relate it. Clear? Now, Sirsa, जैसे आपको बोला जाए कि आपके पास ना किसी एलिमेंट के लिए आपको इलेक्ट्रॉनिक कॉन्फ़िगरेशन लिखना है, जैसे मान लीजिए हीलियम के लिए आप लिखते हैं तो क्या आएगा 1s2. ठीक है, तो 1s2. अब ये s2 कहाँ से आया, तो आपने नॉर्मल इलेक्ट्रॉनिक कॉन्फ़िगरेशन लिखनी है, जो जिस p ऑर्बिटल में आपका लास्ट वैलेंस इलेक्ट्रॉन होगा आप उसके लिए चेक करेंगे. तो ऐसे ही D2 आपको मिलेगा, कहीं पे D8 मिलेगा. ठीक है, तो जस्ट फ्रॉम दैट इलेक्ट्रॉनिक कॉन्फ़िगरेशन. Guys, there is no such definition for Hund's rule. There are points by the Hund's rule which are going to help you to get the ground state spectroscopic terms, and all the points I have mentioned just now, okay, I've even repeated them. So 4 points you can consider. First one we have considered with the multiplicity, second orbital quantum number, third with the angular momentum quantum number, but even the fourth part of this is related to angular momentum quantum number, depending on it is more than half filled case or less than half filled case. Clear? Now, any doubt? I think everything is clear now. हाँ, ओके पायल, जे के लिए एक बार और रिपीट करते हैं. देखिए, and if you need to compare with J values, for example, I will tell you the example now. Is that clear? हाँ, सिरसा इलेक्ट्रॉनिक कॉन्फ़िगरेशन लिखना होगा आपको. सुब्रमण्यम, नॉन इक्विवेलेंट इलेक्ट्रॉन्स केस में जनरली दे विल आस्क यू टू फाइंड द नंबर ऑफ स्पेक्ट्रोस्कोपिक टर्म्स, और दे विल आस्क यू which of the following is not going to exist, or even if any time you need to relate with the ground state, after finding overall all the spectroscopic terms, then with the same rules you will do it. Okay, rules for the ground state are only these ones. Clear? Clear? Okay, let's take some examples now. Let me just give you some more examples to make it more clear to you that how it's gonna work, okay, with some elements and all. So let's take some examples so that you will not face any difficulty and you will easily be able to solve it. Consider I will even tell you a trick right now after just this part, okay, and how to find the spectroscopic terms for the equivalent electrons case. Most probably we will take that point in the next session, upcoming atomic and molecular physics sessions, okay, but right now let's cover up this part mainly. Write the electronic configuration first. हाँ कीर्ति, आपको मैं अभी P3 के इलेक्ट्रॉनिक कॉन्फ़िगरेशंस बताती हूँ, ठीक है, उसमें बिल्कुल कंफ्यूजन और डाउट नहीं होगा टू राइट द ग्राउंड स्टेट. क्यों नहीं होगा? यू विल गेट इट वंस आई विल टेल यू ऑल द स्पेक्ट्रोस्कोपिक टर्म्स. And that is the equivalent electron case. If you want to consider all the spectroscopic terms, then for the P3 case it's gonna be quite lengthy, but there are 3-4 methods we can consider, okay, so I will tell you about that too in upcoming classes. See, last one, P1. How many electrons are there? Just one equivalent electron case. What will be the value of L? L is equal to 1. What will be the value of spin for one electron? Half. What will be the value of J? J is equal to L minus S to L plus S. 1 minus half to 1 plus half. Half and 3 by 2. The gap is of one value only. So you will just consider the two values here. J value you have got. Clear? Next thing. You need to write the spectroscopic term. You know it's going to be 2S plus 1 Lj. Spin is half. So it's going to be 2 into half plus 1, which means 2L. L will be what? It's just P. Okay, for L is equal to 1. Half and 2P, 3 by 2. Now the point is, it is what? It is a less than half filled case. So you can see when you will compare with the multiplicity, that means same, we can't compare it. With the L values, same, we can't compare it. But if I'm going to talk about the concept less than half filled case, lowest state term will have the lowest energy. What is the ground state? 1 by 2 or 3 by 2? 1 by 2. So 2p 1 by 2 is the ground state spectroscopic term. Is that clear to everyone? Clear? Everybody is able to find it now? Done? That's good. Very good. Everybody's answer is correct. Next point. Let's consider oxygen. 8O. Try it and tell me the spectroscopic term for the... Firstly, the first question is number of spectroscopic terms. Then second question I will give you. But first question is number of spectroscopic terms in this configuration you will get. Number of spectroscopic terms. No, total number of spectroscopic terms, not the ground state. Firstly, the total number of spectroscopic terms. Guys, you are writing the total electronic configuration somebody has mentioned, but I am asking about the total number of spectroscopic terms. Total number of spectroscopic terms. Is it just 3? Just 3? Are you sure about it? Let me just consider. It's gonna be 2p4 at the end you will have, and corresponding to that, let me just consider it. Everybody is saying 3 1 3 1. Let's find it out together and let's check. Let me know the last term is p4, yes or no? 1s2 2s2 2p4. Everybody has got that? 1s2 2s2 2p4. Clear? I have told you about, okay, the non-equivalent electron cases. Clear? But now the process we will learn for the equivalent electron case. Okay, I am going to tell you a new method. Now I've got it. Why you are just getting 3 terms? Because you are applying the same rule which is for the non-equivalent electron case. In the previous case, only 1 electron was there, so same process has worked well because only 1 electron was there, and that is same as the non-equivalent electron case process, but it is gonna be different one. Now the first point I am going to consider here is, let me know, is this the equivalent electrons case? Is this the equivalent electrons case? P4. Okay, how many electrons are present there? 4, and also the principal quantum number is same. Also it is present in p orbital, and it is gonna be equivalent electron case. I have told you that the inverted multiplets, which means the D8 and D2 are having the same spectroscopic terms. That means in the same way P4 and P2 will have the same spectroscopic terms. Yes or no? Yes or no about the P4 and P2? Same spectroscopic terms, right? So now you are going to learn a new method to find the spectroscopic terms for the equivalent electron cases, and mainly for the 2 equivalent electron cases, it's gonna be the method that is known as Bright's scheme. Okay, Bright's scheme. How it works? Let's talk about it. It is Bright. Okay, so Bright's scheme, T at the end. Now, if I'm going to talk about that, instead of considering P4, it's better to take P2. It works well for the 2 equivalent electrons case. It works well for the 2 equivalent electrons case. Okay, so I know spectroscopic terms for P4 and P2 will be same. So I can work by considering P2. I need to write the L value first for p orbital. L is equal to 1. Okay, and ML values will be what? So -1 or +1, 0 and -1. Or you can write -1, 0 and +1. -L to +L are going to be the values of ML, magnetic orbital quantum number. When we are considering the role of magnetic field, the splitting will be there, and that's how -L to +L values you will get. Okay, focus on the steps. Now, next thing, as per Bright's scheme, you need to write, and this method works well for the 2 equivalent electrons. It will work well. Even it is there for more than 2 equivalent electrons, but the procedure will get changed. The time taking, it will be more time taking. Okay, but for 2 equivalent electrons, it is the best method. Even for P2, D2, any 2. Okay, but just 2 equivalent electrons cases. So what you need to do, how many electrons we are considering right now? 2. So write for the first electron ML1 for first electron. or the one electron here. For second one, right here, Ml2. What is that? For second electron. Done? How you will write it? All the Ml values we have got, like +1, 0, -1. Same way, same values. Do one thing after this. Consider it like this. +1, +1. What you will get here? Add them, 2. 0 + 1. What you will get here? 1. -1 + 1. Add them, 0. That's what you need to do. What I have done, again I'm just going to show this to you. Vertically and horizontally. That means 1 + 1, 2. 0 + 1 + 1. -1 + 1, 0. Okay, that's how you need to just add the values. +1, 0 + 1. 0, 0, 0. -1, 0, -1. Then +1, -1, 0. 0, -1, -1. -1, -1, -2. Okay, any doubt anybody is going to have in making this? कीर्ति, अगर आपके एग्जाम में मोर देन 2 इक्विवेलेंट इलेक्ट्रॉन्स का केस आएगा तो आपसे ग्राउंड स्टेट पूछ सकता है, और ग्राउंड स्टेट के लिए बहुत सिंपल इजी प्रोसेस है, वो मैं आपको एक्सप्लेन कर दूंगी, ठीक है। और बाकी चांसेस कम है कि वो टोटल नंबर ऑफ स्पेक्ट्रोस्कोपिक टर्म्स पूछे, बट अगर पूछते हैं तो प्रोसेस इज देयर। ओके, सो वी विल इवन टॉक अबाउट दैट इन द अपकमिंग क्लासेस। और सबके लिए प्रोसेस है, मेथड्स हैं, कुछ ज़्यादा टाइम टेकिंग है, जिनसे कभी ज़्यादा क्वेश्चंस नहीं आए हैं। नॉर्मली मोर देन 2 के केस नहीं आए हैं, बट अगर आया भी है तो ग्राउंड स्टेट के लिए। तो ग्राउंड स्टेट की प्रोसेस बहुत सिंपल और ईजी है फिर उस केस में। नो, in this case no modulus, just directly add them. Clear? Guys, let me know for these principal diagonal elements, can you say that Ml1 and Ml2 are same? Ml1 and Ml2 are same for the principal diagonal elements all. 0 के लिए ये 0 था, ये भी 0 था, -2 के लिए -1 था, ये भी -1 था, ठीक है। Same, Ml1 and Ml2 are same for the principal diagonal elements. That means, as per Pauli's exclusion principle, if the orbital quantum number values or Ml1 and Ml2 are same, that means electrons are present in the same state, then their spin should be different. That means, अगर 2 इलेक्ट्रॉन्स सेम स्टेट में हैं तो उनकी स्पिन अलग होनी ही चाहिए, उनकी स्पिन सेम नहीं हो सकती एज पर द पॉलीज एक्सक्लूजन प्रिंसिपल। तो या तो स्टेट अलग अलग है तो आप स्पिन सेम ले सकते हैं, बट स्टेट सेम है तो स्पिन अलग अलग लेनी पड़ेगी, ठीक है। देखिए, सो Ml1 and Ml2 सेम फॉर द प्रिंसिपल डायगोनल वैल्यूज, सो स्पिन विल बी डिफरेंट। व्हेन स्पिन इज डिफरेंट, one half you will take, another one -half you will take, and total spin or the net spin will be 0. Okay. Also, mostly when you are going to apply the Bright's scheme, in the principal diagonal you are going to have the even values. Principal diagonal will have the even values. If you are going to observe all the values, you are getting somewhere 0, you are getting somewhere 1, you are getting the maximum value 2. आपको इस पूरे टेबल में निगेटिव छोड़ दीजिए, क्योंकि वो निगेटिव कहाँ से आता है, इसके लिए होता है, L के लिए, तो निगेटिव इज ऑल्सो जस्ट द वैल्यू ऑफ Ml. बट व्हाट आर द वैल्यूज यू विल हैव? 0, 1 and 2. 0 and 2 even values will be at the diagonal, for which the total spin will be 0. Even spin for even values of L, odd spin for the odd value of L. So इसमें क्योंकि इसके लिए 1 के लिए क्या है, 1 नहीं था, यहाँ पे different values of Ml है. When different values of Ml is there, spin can be same, state is different state. Okay, spin 1. Now you will make the combinations. S is equal to 0 with L is equal to 0 and L is equal to 2. S is equal to 1 with L is equal to 1 and S is equal to 1. And you will get total 5 spectroscopic terms with this. Okay, that is the complete information about the 2 equivalent electrons case spectroscopic term. Clear? Done? So guys, this was the discussion, and just after this make the combination 0 with 2, 0 and 2, the values of L with S is equal to 0, L is equal to 1 with S is equal to 1, even values of L will be considered with the S is equal to 0, and even odd value of L will be considered with the S is equal to 1. Clear? That's how you need to consider it. Clear? So thank you so much everyone for joining the session. I hope each and everything will be clear to all of you, and all the things, all the points, all the topics, whatever discussion we have done in today's session, that will be clear to all of you. Jyoti, firstly consider the equivalent electrons. This method will work well for the two equivalent electrons. Write the ml values, make this type of structure, write ml1 here, write ml2 here. Okay, then after that what you will do, you just need to consider just the sum of this and this together, this and this together, like all the sums you are taking like this in this format. Done. Then whatever values you will have mostly in the principal diagonal element, okay, the elements you are getting, for them spin will be 0. Why? As per the Pauli's exclusion principle, the spin should be different for the electrons which are existing in the same state. For the other values, okay, other than those principal diagonal, you can have the spin 1, because then it is allowed to have the same spin. So only that you need to consider. The principal diagonal में कौन-कौन सी values आएं? 0 और 2. ठीक है, जो even होती है ना वही mostly मिलती हैं प्रिंसिपल डायगोनल में. तो 0 और 2 के साथ स्पिन 0 रहेगी, क्योंकि डिफरेंट स्पिन होनी चाहिए, स्टेट सेम है. और 1 के साथ स्पिन 1, बिकॉज 1 के लिए स्टेट सेम नहीं है तो स्पिन सेम आप रख सकते हैं, तब अलग अलग स्टेट्स में इलेक्ट्रॉन है. ठीक है. So thank you so much everyone for joining the session. I hope each and everything will be clear to all of you. Also guys, if you want to attend the more regular live classes for preparing for the upcoming exam, so you can take the Unacademy Plus subscription also by using and by applying the referral code, that is AnjaliALive, as I have mentioned it here. Okay, no space in between. That's how you need to write it, apply it, and get the 10% discount in the total Unacademy Plus subscription amount. There are so many Unacademy Plus courses going on right now on Unacademy Plus for your upcoming exam preparation. So if you will even take the subscription right now, okay, and any course which is already going on, you have missed any of the classes of those courses, so you will get the recordings of the sessions you have missed, and that's how you will be able to cover up each and everything. Clear? Also guys, for the part A, separate courses are going on, so that's how you will even be able to prepare for the part A very easily, and you will be able to attend the live classes by all the top educators, so which will surely help you to do the best preparation for your exam. And after taking the Unacademy Plus subscription, you will be able to attend the more regular live classes by all the top educators. After taking the subscription, you will get so many benefits like weekly quizzes, doubt clearing sessions, mock tests, PDF of important notes will be available to you, and many more important ideas you will get. You will get to know about the important strategy to prepare for your exam and to score good marks. Clear? So guys, all these things will help you to prepare very well for your exam. If you want to take Unacademy Plus subscription, as it will help you a lot in doing the best preparation, you can take the Unacademy Plus subscription, and whenever you will take the subscription, you can use and apply the referral code, that is AnjaliALive, as I have mentioned it here. Write the spelling as it is, no space in between, apply it, and get the 10% discount in the total Unacademy Plus subscription amount. Thank you so much everyone for joining this session. Thank you. I hope sessions are helping you and you are getting to know about all those important points. Okay, from each and every subject there are going to be some of the topics which are having the great chances to be there in the upcoming exams. So if anybody is going to start the preparation, it becomes very important to focus more and more on those topics and to make a good command on them. And if you are doing it in this manner, you are doing the preparation in the right way and you can score very good marks. Even you can maintain a good rank. So it will be helpful for you. Thank you so much everyone for joining this session. Thank you. Guys, how 5? Okay, let's consider it. How 5 terms you will get. Just a second, let me just tell you. 0, 2 with 0 and 1 with 5. 1 with spin 1 you need to consider, and total terms will be 5. Okay, 0, 2 with 0. With a spin 0. So the J values will be 0 minus 0 to 0 plus 0 and 2. Okay. And L is equal to 1. You are taking with the spin 1. Okay. So 1 minus 1 to 1 plus 1, because J is equal to L minus S2, L plus S, which means 1 minus 1 to 1 plus 1, 0, 1, 2, 3, 4, 5 total. Done? So that's how you can write it. Is this clear now? Done? 5 are the total spectroscopic terms. So when you will write them, these are the J values, this is the L value. So for S, L is equal to 0, S. For L is equal to 2, SPD. Okay, for L is equal to 1, it's P. 2S plus 1, 2 into 1, 0 plus 1, 1S. 1D, 2 into 1 plus 1, 3. It's going to be J value 0, 2, 0, 1 and 2. 3 terms from here, 4 and 5. Clear? Thank you so much everyone for joining this session. Thank you.